All right, kiddos at home, you obviously are going to miss out on the lab that we did in class, which was like a hands-on lab, a little bit of discovery learning, and also making sure that the real world mimicked what we knew theoretically when we were talking about formulas for density. But I did want to get something at least together for you so that, and change the color, so that you had something to look over. So what we were doing is density, and the reason why we were doing density is because in the formula for density, you actually have the volume of an object, and we just finished a whole chapter on volume. So let's go ahead and do the start thinking part first. The question is, what is heavier, a pound of lead or a pound of styrofoam? I remember thinking I was so clever when I would ask this to my friends when I was back in elementary school, and most kids would accidentally say styrofoam. They would say styrofoam was obviously, or sorry, they would say lead because they thought that styrofoam was lighter, so therefore lead must be heavier. But what they didn't pick up on was I said a pound of lead and a pound of styrofoam. So if it's a pound of lead and a pound of styrofoam, then they're obviously going to be the same exact weight. Now, the issue here, and what we're going to be looking at today, what they were thinking was a pound of lead is going to be much more compressed. You can get a pound of lead in a small volume, whereas a pound of styrofoam is going to be much, much bigger when we're looking at the volume that is going to end up being that same exact weight or mass. So why is that? It's because lead is very much more, it's going to be much, much more dense than styrofoam is. So a very crude definition of density would be the amount of stuff in a certain space. Now the space that we're going to be talking about is going to be a cube that is 1 centimeter by 1 centimeter by 1 centimeter. So the volume would be 1 cubic centimeter, or 1 cc. All right. Now you can kind of figure out how much stuff is able to actually fit inside there. So let's go ahead and take a look at the mass, what we're going to be measuring our mass in. And we're going to be measuring it in grams. So I do want to make sure you guys understand what a gram is. We're so used to in the US using ounces and whatnot to measure ounces and pounds. But in the 1700s, there were some people in France who decided to come up with a different measurement system. And what they had to do while they were doing this, developing the metric system, is they had to find a unit that they were going to measure mass in. So what they came up with was the gram. What a gram is going to be is how much of a certain substance fits inside of this 1 by 1 by 1 cube. So they had to figure out what substance were they going to put in there. Should they put gold? Should they put iron? What should they put in? What they decided to put in there was something that is a substance that pretty much everybody has access to, and that's water. So 1 cubic centimeter of water is going to be a gram. Now that is if it is a cubic centimeter of pure water, and I forget what the exact temperature is. I think it's like 4 degrees Celsius or something like that, but it will be exactly 1 gram. Then they had to figure out a way to measure liquids. They've already started talking about how they could measure solids. So they came up with a milliliter. And what we ended up having was 1 milliliter was actually equal to 1 cubic centimeter of water, which was equal to 1 gram. So all of those things are equal, and we're going to use that in today's lesson. So the formula for density is going to be density equals the mass, the amount of stuff that fits in a certain volume. This is going to be in grams, and this is going to be in cubic centimeters. Also, you could think of it as milliliters. Okay? When you think about this and you want to think of the density of water, let's say we had 1 gram of water, 1 gram of water. How many cc's is that going to be? Well, we just learned 1 cc of water is 1 milliliter is 1 gram. So it's going to also be 1 cubic centimeter or 1 milliliter. You can think of it either way. And what we end up getting is the density of water is exactly 1. Now, our lesson could be thought of as does it float or does it sink instead of the density lab, because a lot of what we did in class was just figuring out, is an object going to float or is it going to sink? And the way we did that was if something had a density that was less than 1, it floats. If it has a density greater than 1, it is going to sink. Okay? And if it is 1, it's just going to basically be 1 with the water. Now, what's really, really cool about this is you can go beyond just figuring out if it floats. You can kind of look at the object, if it's a uniformly shaped object, and figure out what the approximate density is just by seeing how much is under the water. So for example, here, let's say this was 1 inch and this was 2 inches. Well, we can see 1 out of the 2 inches is underwater, which is 0.5, and we'd be able to tell that this thing has an approximate density of 0.5. On the other hand, let's say this was 1 and the whole entire length or the whole entire height was 4, and this was a uniform, densely figured figure, and it's a uniformly shaped figure, meaning like if you're looking at, let's say, a sphere, if like maybe a 2 millimeters is above water, well, this 2 millimeters up here is going to have less material than the 2 millimeters down here. So it's a little bit more tricky if the shape is not like a rectangular prism. But on this one, we're pretending like this is a rectangular prism. Well, since 1 of the 4 inches is underwater, then that means that 25% is underwater, and it's going to have a density of 0.25. Now, when we look at something like this, though, you can see that the whole entire thing is underwater. It's resting on the bottom. And you might think, well, can we figure out what that density is? We know it's going to be greater than 1. Well, realistically, if the object is just sitting on the bottom, we don't know if that has a density of 1, if it has a density of 10, 100, who knows what the density is going to be. We just know, actually, we know it's definitely not going to be 1. Maybe it's 1.1 or 10 or 100. All we know is that it sank through the water and it ended up at the bottom. Okay, so that's just a little bit more tricky. But when it's actually floating, you can kind of figure out what percentage is underwater, and that will give you an approximate density. So what did we end up doing? In class, we had an object. We had an object such as I had a piece of wood. They were able to set it in the water and see if it floated. Let's say it floated. You would say yes. Then you go over and figure out, does that mean that it has a density more than 1 or less than 1? And it would be less than 1 if it is floating. Now the density guess, the way that they did this was they did this method over here. They just tried to take a guess at what percentage of the object was underwater. And if it was a huge percentage, for example, they did it in orange once and it looked like about 95% was underwater, then it had a density about 0.95. Now when it came to a calculated volume versus a displacement volume, let me explain that. If we had a rectangular prism like this, I wanted the students at least once to measure out in centimeters and figure out what the calculated volume was. So let's say they figured out that it was 30 centimeters cubed. Now let me explain this whole displacement volume deal. We know that a cubic centimeter is equal to a milliliter. So what the students did for most of the problems is they just had a graduated cylinder and they filled it up to, let's say, 100 milliliters. And then they went over and put their object in there. And some of the object was out of the water. So what they did was they pushed down until the whole entire object was underwater, but not like their finger or anything was under the water, just the object. It was basically in line with the water. Once they did that, they would figure out where the water went to. And let's say it went to 125 milliliters. Well, you can see the difference here was 25 milliliters, and since a milliliter equals a cubic centimeter, they were able to find the volume that way. This is super, super helpful if, let's say, you had a shape that looked like this, like some weird rock. Well, this obviously doesn't have a shape that we have found a formula for the volume. So rather than going over and having to break this up into a bunch of different spheres and whatnot, what you could do is you could just put 100 milliliters of water in, drop this in. If it sinks, you don't even have to push it down underwater. It's just easier. When it's down at the bottom, then you figure out what the difference in the milliliters is, and that's going to give you your volume. And this is all because of the people who thought up this method had a milliliter equaling a cubic centimeter, which is pretty awesome. So anyways, let's say both of these, they got 30 centimeters cubed. And then they went over and got a mass of, let's say, 20 grams. And the way they did that was I borrowed some scales from the science teachers. And we know density equals mass over volume. and they would go over and do your division. So in this case, it would be 20 over 30, which is 0.66. And then they just asked themselves if this made sense. This is less than 1. It was supposed to float, and yes, it did float. Then they would go over and actually check their density guess. So this would have meant the object should have been about 66% under the water. So they were able to actually check if their density guess by looking at the object was correct or not. And that's what they did. They had wood, they had like this block of plastic, they had a little orange, they had a piece of styrofoam. The styrofoam was like barely underwater, and a lot of them guessed, okay, about 3% is underwater. And when they found out their displacement volume, I didn't have them do this volume with a ruler, they just were able to do the displacement volume. And they found out what the mass was in grams. It sure enough was very close to like a density of 0.03 or something like that. So that is basically what we were doing. We were talking about things that were less dense than water and they floated, or more dense than water and they sank. And the cool thing here is you can actually look at this with air as well. We could figure out what the density of air is. And then, for example, a hot air balloon, the reason why a hot air balloon is going to rise is because the hot air is going to be less dense than the cool air. So the hot air wants to get on top of the cool air because it's less dense and it'll go up. Same thing with helium. Helium is less dense than air. So you could actually look at that. One last thing that I found really interesting, I was looking up the weight of air, because obviously we move air around all the time, and I couldn't figure out what the weight was. I figured it was like a gram for a large amount of air. So I looked it up and it said 1 meter by 1 meter by 1 meter of air was actually something like 1.2 kilograms, which is like high twos, so maybe like 2.8 pounds or something. And that seemed like it was crazy. Like no way could it weigh that much. So anyways, and I know science teachers this would drive them crazy with me using the word weight instead of us talking about mass. But anyways, I was thinking like this doesn't make any sense because if I had a bag with that much air in it, it would not feel like almost 3 pounds. And what I realized was the reason you wouldn't feel that was because this bag of air would be suspended in a medium, more air, that was the same exact density. It's kind of like if you were in a pool and you had I don't know, a jug of water that was sealed off and you were trying to carry it on land and then you put it in the water and you got underneath and you were kind of lifting it up and you would realize, wow, this is really, really not heavy. And it's because the water is suspended in water. Same reason why they recommend that older folks do like their exercises in a pool. Our body is mostly water. And if you're in the water, then you probably notice that your body does not feel like it weighs much when you're in the water. So anyways, what you guys are supposed to do for homework is this. We have two parts to the homework. This part right here is just like a conceptual part, seeing if you understand the concept of density and things floating and sinking. I'll go ahead and do the first one with you. So this says, if I blow out all my air in a pool, I sink. I'm like a pretty skinny guy, and I start sinking. So the question is, what does that tell you about my density? What that tell you about my density is my density must be greater than 1. Now, I don't sink very, very quickly, and my body is mostly water, so that makes sense that my density is more than 1, but not much more than 1. Okay? And 1 is obviously the density of the water, which is why I would sink. Now, the part B says, when I breathe in and get my lungs full of air, I can float. What is the scientific reason for this? Now, when you think about this, density equals mass over volume. In the situation here, you got to figure out what is changing. If I'm in the pool and I breathe in a bunch of air, my mass doesn't really change. Yes, the air that I breathe in has a little bit of mass, but not that much. So something else has to change. I'm still my, I don't know what I am in kilograms. Let's say I was 70 kilograms or something like that. I'm still 70 kilograms. So what has to change to make my density less would be the volume. Think about my body. When I breathe in, the total volume that my body is taking up is going to become bigger. And we all know if you had a fraction and you go over and increase the denominator, let's say you increase that to 4, then the overall number gets smaller, which means the density gets smaller and I become more buoyant. So what I want you guys to do is go ahead and answer these questions, and then you have a few questions over here also that are more computation based. And feel free to let me know if you have any questions, and I can answer those when you're in class. Thanks a bunch for watching.